Hello students, in this class we will learn arithmetico-geometric progression. Okay, so what do you mean by arithmetico-geometric progression? Arithmetico-geometric progression is a series where every term is the product of the terms of an AP as well as a GP. Okay, so let us study what do you mean by arithmetico-geometric progression. If we follow an example of a series like 1 plus 2x plus 3x squared plus 4x cubed plus continuing, then here first term a1 equals to 1, second term a2 equals to 2x, third term a3 equals to 3x squared, fourth term a4 equals to 4x cubed. Then we can write this a1 first term as 1 into 1. Second term a2 as 2 into x. Third term a3 as 3 into x squared. Fourth term a4 as 4 into x cubed. So like this way this series of value continues. Then if we follow the first terms of these every terms, then they will form an AP. Now the first terms of every terms of the series are 1, 2, 3, 4 continues, and the second terms of every terms of the series are 1, x, x squared, x cubed continuing. Then these first terms forms an AP. These first terms forms an AP, and these second terms forms a GP. Okay, so if we follow the first terms of this every term of the series, then these first terms are 1, 2, 3, 4 continuing. So these first terms forms an AP. And if we follow the second terms of this every term of the series, then the second terms will form a GP. That is why we can say every term of this series, that is 1, 2x, 3x squared, 4x cubed, every term of this series is the combination of the terms of an AP as well as a GP. So this is known as an arithmetico-geometric progression. Okay, so we can create a definition. if a series of value progressed in such a way that every terms is the product of the combination of the terms of an AP as well as a GP, then that progression is known as an arithmetico-geometric progression or AGP. Okay. So, if a series of value progressed in such a way that its every term is the product of the terms of an AP as well as a GP, then we can say that progression is an arithmetico-geometric progression or an AGP. Okay. General form. Sn equals to a plus d whole into r plus a plus 2d whole into r square plus a plus 3d whole into r cube plus continuing plus a plus n minus 1 whole into d into r to the power of n minus 1. So, this is the general form of an AGP. Here Sn represents sum of n terms of this AGP. Okay. So, here the first term A1 is A, second term A2 is A plus D into R, third term A3 is A plus 2D into R square, and continuing, and this represents nth term of this AGP, that is A plus n minus 1 whole into D whole into r to the power of n minus 1. First terms of the series are A plus D, A plus 2D, continuing. Second terms of the series are 1 x square, continuing. Okay. So, these are the first terms of this series, that are A plus D, A plus 2D, A plus 3D, continuing, and the second terms of this series are 1 A means we can say A into 1. So the second terms of the series are 1 r square, 1 r square, continuing. Okay. So individually the first terms form an AP and the second terms forms a GP. Here the common difference is D and first term is A, and for this GP common ratio equals to R. Okay. Now if we want to find the sum of these n terms of this AGP, then we have to follow some procedure. Okay. Then let us follow the procedures. This is number 1. Multiplying both sides of 1 by the common ratio R, we get R into Sn equals to AR, A into R, AR, plus A plus D into R square, plus A plus 2D into R cube, plus continuing. The second last term of this series is second last term, that is A of n minus 1 is equals to A plus n minus 2 whole into D whole into R to the power of n minus 2. Okay. So this is the second last term of this series. Now if we multiply this term by the common ratio R, then this will give A plus n minus 2 whole into D into R to the power n minus 1. And when this last term of the series is multiplied with the common ratio R, then this will give A plus n minus 1 whole into D into R to the power n. This is number 2. Now to get a simplified form of the sum of n numbers of terms of this AGP, we have to follow some procedure, and at first we have to multiply all the terms of this relation by the common ratio R, and after multiplying all the terms by this common ratio R, we get R into Sn equals to AR plus A plus D whole into R square plus A plus 2D whole into R cube plus continuing, and the second last term of this AGP is A plus n minus 2 whole into D into R to the power of n minus 2. When this is multiplied with the common ratio R, then we will get this, because this into R will give, this will remain same, and this will be r to the power of n minus 2 plus 1 will give r to the power of n minus 1, and the last term becomes this. Okay, we arrange these terms as per the powers of r. Subtracting 2 from 1, we get Sn equals to, Sn minus r into Sn equals to a plus d into r minus ar plus a plus 2d into r square minus a plus d into r square plus a plus 3d into r cube minus a plus 2d whole into r cube, plus continuing this way, plus a plus n minus 1 into d into r to the power of n minus 1 minus a plus n minus 2 whole into d into r to the power of n minus 1, and the last term becomes minus of a plus n minus 1 whole into d into r to the power n. Okay, this will give, we can take Sn as the common factor from these two, and the rest of the terms becomes Sn into 1 minus r, and the right hand side of and the terms of the right hand side becomes a plus. We can take r as the common factor from these two, and after taking r common from these two, we get this plus a plus 2d minus of a plus d into r square plus from these two a plus 3d minus of a plus 2d whole into r cube, plus continuing plus a plus n minus 1 whole into d minus of a plus n minus 2 whole into d into r to the power of n minus 1, because in these two terms r to the power n minus 1 is a common factor. That is why we can take r to the power of n minus 1 from these two as common, and the rest of the terms becomes a plus n minus 1 whole into d minus of a plus n minus 2 into d, whole into d. So this whole into r to the power of n minus 1, and the last term becomes minus of a plus n minus 1 whole into d into r to the power n. This implies Sn into r minus 1 equals to a plus, cancelling these two, we get dr. A plus 2d minus a minus d whole into r square plus a plus 3d minus a minus 2d whole into r cube plus continuing plus a plus nd minus d minus a minus nd plus 2d whole into r to the power n minus 1 minus of a plus n minus 1 whole into d into r to the power n. We can cancel these like terms. Then we get Sn into 1 minus r equals to a plus dr plus dr square plus dr cube plus continuing plus d into r to the power n minus 1 minus of a plus n minus 1 whole into d, this whole into r to the power n. Okay. So we get Sn into 1 minus r equals to a plus dr plus dr square plus dr cube plus d into r to the power n minus 1 minus a plus n minus 1 whole into d, this whole into r to the power n. Okay. So this implies Sn into 1 minus r equals to a plus. Now if we follow these terms, then d is the common factor among these terms. Okay. So we can take d as common from these terms, and the terms becomes d into r plus r square plus r cube plus continuing plus r to the power n minus 1 minus of a plus n minus 1 whole into d, this whole into r to the power n. So Sn into 1 minus r equals to a plus d into, now these terms r, r square, r cube continuing up to r to the power continuing the and the last term r to the power n minus 1 form a GP, where the first term is r, common ratio is r, and there are n minus 1 numbers of terms. These forms a GP where first term A1 equals to R, common ratio common ratio, that is shortly represented by CR, is equals to smaller and number of terms equals to n minus 1. So the sum of these terms is first term into r to the power of n minus 1 minus 1 whole divided by r minus 1 minus of a plus n minus 1 whole into d, this whole into r to the power n. Okay. So we find the sum of this GP by following the formula of summation of a GP, where the first term A1 is smaller, number of terms is n minus 1 and the common ratio is smaller. That is why the GP summation formula is A into r to the power n minus 1 whole divided by r minus 1. So by following this formula, we represent this sum as dividing both sides by 1 minus r, we get Sn equals to A by 1 minus r plus dr into r to the power n minus 1 minus 1 whole divided by r minus 1 into 1 minus r minus a plus n minus 1 whole into d into r to the power n whole divided by 1 minus r. Dividing both sides by 1 minus r. Now we can write this 1 minus r as minus of r minus 1. Okay, as 1 minus r is equals to minus r plus 1. When we take minus as the common factor from these two, we get minus of r minus 1. So this will give Sn equals to A by 1 minus r plus dr into r to the power n minus 1 minus 1 whole divided by r minus 1 into minus of r minus 1 minus a plus n minus 1 whole into d into r to the power n whole divided by minus of r minus 1. So this implies Sn equals to A by 1 minus r. This minus when multiplied with this plus, we get minus dr into r to the power n minus 1 minus 1 whole divided by r minus 1 whole square minus, when this minus is multiplied with this minus, we get plus a plus n minus 1 whole into d, this whole into r to the power n whole divided by r minus 1. Okay, so this is the representation of sum of n numbers of terms of an AGP, where r not equals to 1 and we consider r as greater than 0. Okay, so this is the representation of sum of n numbers of terms of an AGP, where r is not equals to 1 and we consider r greater than 0. Okay. When n tends to infinity and minus 1 less than r less than 1, then r to the power n that is r to the power infinity tends to 0, then s of infinity is equals to 1 by 1 minus a by 1 minus r minus d into, we can multiply these two. So r into this will give r to the power n minus r whole divided by r minus 1 whole square plus a plus n minus 1 whole into d, this whole into 0 whole divided by r minus 1. So when n tends to 0, that is number of terms of this AGP becomes infinite, then and r belongs to this range, that is r is greater than minus 1 and lesser than 1, then r to the power n, that is r to the power alpha tends to 0, because if we choose r equals to half, then half whole square means 1 by 4, half whole cube means 1 by 8, half whole to the power 4 means 1 by 16, that is its value gradually decreases. So when it continues this by this way up to infinite terms, then r1 r to the power infinity will be very small. That is why we can consider that very small quantity as 0. That is why we write r to the power infinity tends to 0. And by following this, so this formula becomes this. And finally, we get s of infinity is equals to a by 1 minus r minus d into 0 minus r whole divided by r minus 1 whole square, and this whole thing becomes 0 because 0 into something will give 0, and this will give s of infinity is equals to a by 1 minus r plus dr by r minus 1 whole square. Okay. So when the number of terms of an AGP continues up to infinity and smaller is greater than minus 1 and lesser than 1, then we can find those infinite terms by this way, that is s infinity equals to a by 1 minus r plus dr by r minus 1 whole square. Here we choose a problem. For this problem, we have to find the sum of n terms of this series, and the series is 2 into 1 plus 3 into 2 plus 4 into 4 plus 5 into 8 plus continuing. So if we follow the terms of this series, then they are: first terms of every terms are 2, 3, 4, 5 continuing, and the second terms of every terms are 1, 2, 4, 8 continuous. So these form an AP. 3 minus 2 equals to 1. 4 minus 3 equals to 1. 5 minus 4 equals to 1. So these terms forms an AP and these terms forms a GP because 2 by 1 equals to 2. 4 by 2 equals to 2. 8 by 4 equals to 2. So every terms of this series is the combination of terms of an AP as well as a GP. That is why we can say this is an AGP or arithmetico-geometric progression. Okay. So here A, that is first term of this, is 2. Common difference D is 3 minus 2 equals to 1. And for this, common ratio R is equals to 2 by 1 equals to 2. Now, to find the sum of n terms of this series, we have to apply this formula. So, the given series is an AGP as its every term is the product of terms of an AP and a GP. Okay. So therefore, sum of n terms of this series is equals to series is Sn equals to A by 1 minus R minus dr into R to the power n minus 1 minus 1 whole divided by R minus 1 whole square plus A plus n minus 1 whole into d, this whole into R to the power n whole divided by R minus 1 imply Sn equals to A means 2, R means 2 minus D means 1, R means 2. To the power n minus 1 minus 1 whole divided by 2 minus 1 whole square plus A means 2, 2 plus n minus 1 into D means 1 into 2 to the power n whole divided by 2 minus 1. Okay. So 2 by 1 minus 2 minus 1 into 2 into 2 to the power n minus 1 minus 1, 2 minus 1 whole square plus 2 plus n minus 1 into 1 divided 2 minus 1 into 2 to the power n. So these imply Sn equals to 1 minus 2 means minus 1, 2 by minus 1 minus 2 minus 2 into 2 to the power n minus 1 by 1 square plus 2 plus n minus 1 into 2 to the power n by 1. So these imply Sn equals to minus 2 to the power n plus 2 plus n plus 1 whole into 2 to the power n, cancelling plus 2 minus 2 we get Sn equals to n plus 1 whole into 2 to the power n minus 2 to the power n. So after simplifying, we get sum of n terms of this AGP equals to n plus 1 whole into 2 to the power n minus 2 to the power n. Okay, so this is the way by which we can find the sum of n terms of an AGP. So to find the sum, first of all we have to identify that is an AGP. Okay, then after identifying that series as an AGP, we have to find the sum by following this formula. Now we will learn harmonic progression or HP. So what do you mean by HP or harmonic progression? If we follow the example of this series, then the terms are: first term A1 equals to half, second term A2 equals to 1 by 3, third term A3 equals to 1 by 4, fourth term A4 equals to 1 by 5, continues. So there is no specific relations between these terms. Okay, but if we find the reciprocals of these terms, reciprocals of the terms are: reciprocal of half is 2, reciprocal of 1 by 3 is 3, reciprocal of 1 by 4 is 4, reciprocal of 1 by 5 is 5. Continues. Then 3 minus 2 equals to 1, 4 minus 3 equals to 1, 5 minus 4 equals to 1. That is, any term minus its previous term gives a fixed value. That means the reciprocals of the terms forms an AP. Okay, so if a series of value progressed in such a way that their reciprocals forms an AP, then we can say that series is, or the progression is known as an harmonic progression. Okay, or in short HP. Definition: if a series of value progressed in such a way that the reciprocals of the terms forms an AP, then that progression is known as an harmonic progression. Or HP. Okay, so if a series of value progressed in such a way that the reciprocals of the terms forms an AP, then that progression is known as an harmonic progression. Okay. Here we choose a problem. In this problem, a series of value is given. Okay, that is 1 by x minus 3y, 1 by x minus 2y, 1 by x minus y, 1 by x continuing. We have to prove this series is an HP. This series is a HP. That is, the terms of this series follows a harmonic progression. Okay. Solution. Here, first term a1 equals to 1 by x minus 3y. Second term a2 is equals to 1 by x minus 2y. Third term a3 is equals to 1 by x minus y. Fourth term a4 equals to 1 by x. So, reciprocals of the terms are, reciprocal of this is x minus 3y, reciprocal of this is x minus 2y, reciprocal of this is x minus y, reciprocal of 1 by x is x. Continue. Now, x minus 2y minus of x minus 3y equals to x minus 2y minus x plus 3y. Cancelling x, minus 2y plus 3y will give plus y. X minus y minus of x minus 2y equals to x minus y minus x plus 2y. Cancelling this x, minus 2y plus y will give y. Minus y plus 2y will give y. X minus of x minus y is equals to x minus x plus y. Cancelling this x, we get y. That means every term minus its previous term always gives the fixed value. So these imply the reciprocals of the terms of the given series forms an AP. Therefore, by the definition of HP, we can say the given series is a harmonic progression or HP. Good. So, this is the way by which we can identify a series. That means that series of value is a HP or not. Okay.